Welcome to this particular session. I am Zamir Sheikh, Faculty of Chemistry from Shri Shivaji College of Arts, Commerce and Science, Kolkata. So today we'll going to discuss the main principles, their applications of crystal field theory. So as per the university syllabus, these are the some contents which we'll going to cover in this particular session. So before that, I'm just giving some the points which are mentioned in our syllabus. So basically what the first is postulates, then the CFSE, that is crystal field splitting in octahedral, then distorted octahedral, square planar, tetrahedral complexes, the concept of what crystal field splitting energy or the stabilization energy, high spin and what low spin complexes, their pairing energy, and the distribution of what electrons in different splitted energy level, example T2G and EG. Then what are the factors which are affecting on to the crystal field stabilization energy or the crystal field splitting in particularly the octahedral complexes. Okay, so the crystal field theory which is explained by Hans Bethe and Van Vleck. So this theory is put forward by Hans Bethe in 1929 and Van Vleck 1935. So before proceeding to the crystal field theory, we must know the failures of valence bond theory. Okay, the valence bond theory have some limitation, and due to that reason the crystal field theory is arises. Okay, so the first failure of valence bond theory is they cannot explain how tetrahedral or square planar complexes are going to be formed. One can say the failure of valence bond theory is the distortion in the complexes. Okay, then next one, color of the complexes, that is called as optical spectra. And one more important failure of the valence bond theory is the temperature dependence magnetic properties. These are the four important failures of the valence bond theory. Okay, valence bond theory is put forward by Linus Pauling in 1930. Okay, while after that 1930s again or the same era, the CFT will there now, or CFT is proposed by Bethe and Van Vleck. Okay, and the applications of crystal field theory to the chemical system or to the chemical compounds in 1950s. Now this theory is basically related with the ionic nature, related to one ionic nature of metal and ligand. This theory is involved the electrostatic approach, particularly to the word bonding complexes, and this involved metal and ligand is a purely ionic character. The crystal field theory is often termed also as a ligand field theory. What are the postulates of the crystal field theory? The main assumptions in the crystal field theories are there is an interaction between metal ion and the ligand is purely electrostatic. That is, ligands are treated as a point negative charges and metals are treated as a positive nuclear system. So there is an attractive forces between them, and that's why the metal ligand interaction is said to be the purely ionic. Okay, so this central metal atom is surrounded by the point charge or point dipole ligand, and the bonding between metal cation and the ligand is arises due to the electrostatic force of attraction. These interaction between the electrons of cation of one more thing is there is also what the repulsion is there now. Okay, attractive forces is there because of what metal cation and the ligand, but simultaneously metal also have some electrons. That electrons is going to repel with the ligands. So there is a repulsive forces are also be there now. Okay, and due to that reason the d orbital which are that means which are in a degenerate state, that is all 5d orbitals are in a same energy level, that is called the degenerate level, they may get into splitted now. Okay, and that's why there is a splitting is going to be occur. Okay, so basically a crystal field theory which does not explain or which does not involve any kind of an overlap, which is like to be in valence bond theory. Okay, this is the basic difference between the CFT and VBT. Okay, so simple way, the metal ion is going to interact with the ligand. Okay, and there is an interaction between them that will lead to the formation of a complex. Okay, now before proceeding to this, okay, before proceeding to the complex formation, you must understood how the orbitals are going to be classified. You know that these d orbital are of same energy level, that is called as a dxy, dyz, dxz, x square minus y square and dz square. Now out of this 5 orbital, the 3 orbital are said to be non-axial and 2 orbital are said to be the axial. Now what is meant by axial and what is meant by non-axial? So here dz square and dx square minus y square. Look at the pictures now. Okay, they are lobes which are present along the axis. They are lobes which are present along the axis. That's why they are said to be the axial orbital. And what is present in the lobe now? Electron density. Okay, so the electron density which is present on axis or the lobes which are directly orient on the axis, that orbitals are said to be called as a axial orbital, while dxy, dyz and dxz, their lobes are in between the axis, that's why they are said to be the non-axial orbitals. Okay, so this is the basic difference between axial and non-axial orbital. Okay, before the interaction of the ligand, all the 5d orbitals are on a same energy level, that is called as a degenerate energy level. Okay, so how the splitting is going to be occurred now? Let's say the example of octahedral complex. You know that this is an octahedral complex where 6 ligands are coordinated with the central metal ion. Okay, now, so this is what the 3d orbitals particularly for a free metal ion before the application of what ligand. Whenever the ligands are just interacted with the metal ion, the metal d orbital raise their energy now. And suppose let's say example, these are the orbital xy, yz, xz, z square and x square minus y square. Out of this, these two orbitals are called as a axial. Their basically what? Their lobes are present on axis, while these are called as a non-axial. Okay, they are said to be non-axial. Now here these ligands are orient from the axis. Let's say this is what the orientation of the ligands now. The ligands are interacted through the axis, and now these axial orbital are interacted with the ligand. So now these orbitals also have electron density and ligand also have electron density. So now during the metal ligand bond formation, the metal ligand bond is a purely ionic in nature like this one. Okay, now this is the first interaction, that is called as a attractive forces between cation and anion. Okay, beside that, the axial orbital of a metal is going to undergo the repulsion with the ligand, and that's why there are two set of orbital, that is called as a dz square and dx square and y square. They raise their energy. Okay, and while dxy, yz and xz basically they are lower their energy because of for the stabilization. Okay, and now the splitting of the degenerate orbital into the two different set, that is called as a crystal field splitting. Okay, why it is called as a EG? So basically that E stand for two dimension, okay, and G stand for it is a Girard. So Girard is nothing but the centrosymmetric. Okay, what about the T2G now? T2G stand for triply degenerate orbital or three dimension. Okay, and again G stand for what? The Girard. Okay. Now how the mechanism is going to be proceed, I will just demonstrate you. Look at this metal, and before interaction with the ligand, okay, the all 5 d orbitals are of equal energy, but when the ligands are suddenly interacted with the metal ion, there is a splitting is going to be occur now. That's why it is called as a crystal field splitting. Now look at the tetrahedral complex. In a tetrahedral complex, there is a complete opposite system is there now. Because in tetrahedral complex, there are only 4 ligands are there. You can see the geometry here, okay. And that in a tetrahedral geometry, tetrahedral molecules are, they are non-planar, okay. So no one orbital is present on an axis, okay, and that's why in this case in a tetrahedral system the ligand orbital or ligands are orient from in between the axis now, and that's why those orbitals are said to be the non-axial orbital. They are, okay, undergo the what more repulsion now, that's why they will raise their energy now. Okay, so generally the T2 stand for, again it is similar to that of your octahedral system, but we cannot mention G because G stand for centrosymmetric. Here these tetrahedral molecules are non-centrosymmetric, so must consider the difference between the tetrahedral and octahedral. Okay, so for a free metal ion, all the 5 set of d orbitals are degenerate state, but whenever the ligands are interacted, there is a splitting is going to be occur. The next important part is called as a CFSE, that is called as a crystal field stabilization energy. Now the crystal field stabilization energy is basically arising due to the splitting of the d orbital, okay. And for octahedral complexes we have CFSE is equal to minus 0.4 into number of electrons in the T2G level plus 0.06 into number of electron into the EG level, okay. And this del 0 is basically the splitting, and this is what mean pairing energy, okay. So that will be equals to 4 into number of electrons in T2G and plus 0.6 into number of electrons in EG, okay. And this is what dq plus what the MP, that is called as a mean pairing energy. This is for what? Octahedral complex. Now for the tetrahedral complexes, we have the reverse case is there. That's why the 0.6 minus 0.6 into the number of electrons in E level plus 0.4 into the number of electrons in what the T2 level, okay. And by using that formula, we can find out the crystal field stabilization energy. Now what are the factors that are affecting onto the word CFSE? The first of all, higher the oxidation state of the metal atom, the larger the value of del O. What does it mean higher the oxidation state? Let's say example, the cobalt in +2 state and cobalt in the what +3 state now. So here cobalt +2 means the larger in size and cobalt +3 means smaller in size. So here larger in small size and large size. Let's say this example. Now the size is small but charge is more, so ligand will be attracted very strongly, okay. So that's why the splitting will be more. So look at this number now. For a cobalt 2 complex, the del 0 value is 10,200 per centimeter, while for a CO3 complexes the value will be equals to 22,870 per centimeter. So if the metal with maximum positive charge, so it will be the attractive forces for that particular will be the more. Okay. Second one, the nature of transition series. Okay. From top from let's say example 3D, 4D and 5D. For a 3D, okay, 4D and 5D, the nuclear charge is going to increase now. So the attractive power toward the ligand is also what increases. Okay, that's why the values also increases now. Geometry is also important. You know that in octahedral complexes there are 6 ligands are there. So the interaction will be more and also what? The splitting is also more. For tetrahedral complexes only 4 ligands are there. So interaction will be less, the splitting also what less now. And the last one, the nature of ligand. It is decided by spectrochemical series now. Okay. And in spectrochemical series, in very shortly, carbon donor, nitrogen donor, oxygen donor and halogen donor. If carbon donor ligands are there, the splitting will be more, then nitrogen, then oxygen and then what? Halogen now. So as per chemical, the spectrochemical series, the splitting value is also decided. Okay, these are the important factors. Next to that, you know the spectrochemical series. This is what the whole spectrochemical series. Okay, and based on that, now strong field ligand means what? The ligands which are very strongly interacted with the metal ion, due to that reason repulsion will be more, the splitting will be more now. So whenever ligands are a strong, say example carbon donor ligands are strong field ligand. So generally that type of the complexes are called as a low spin complexes. While weak field ligands, nothing but the ligands are interacted weakly with the particular metal ion. So the splitting is also less and that will be called as what? High spin complexes. Okay. So based on that we have carbon donor, nitrogen donor, oxygen donor and halide donor. Next to that, how to distribute that electrons in T2G and EG level, particularly for high spin and particularly for a low spin. So let's say example, high spin means more number of electrons are unpaired, or low spin means the maximum number of electrons are paired now. Okay, we have to obey the Hund's rule, that is electrons should be filled singly first, then pairing is going to start. Okay, and whenever the ligand is weak field, we have to obey Hund's rule. Whenever a ligand is a strong field, we have to violate the Hund's rule, right? So very simple. Let's say example for a D5 system. So for a D5 system, I have two types of what complex. Let's say example the MnCN6, okay, 4 negative, and one more example is MnH2O6 2 plus. Both are complexes of what D5 state, right? Now we have 5 electron. So let's say this MnCN6 is belong to this category and water is belong to this category. Okay, because cyanide is a strong field ligand. So whenever a strong field ligand is there, we have to pair all the electrons. That's why maximum electrons are paired, while whenever this water halogens are the ligand, these are called as a weak field ligand. So we have to start Hund's rule now. We have to obey the Hund's rule. Okay, and these are the crystal field stabilization energy, particularly for the high spin and particularly for the low spin complexes. What are the applications of our crystal field theory? It predicts the type of a geometry, let's say octahedral, tetrahedral. It predicts the type of a ligand or type of the complex, whether it is high spin or the low spin. We can interpret the type of what complexes on the basis of what the color. Also the hydration and what the lattice energy can be find out. This is important basically how to predict the one can say the color. What are the limitation of what CFT? CFT gives a total emphasis of the ionic and partial covalent character of metal bond is not considered. That is, in CFT only ionic character is going to be considered. So CFT consider only d orbital. It cannot consider the which Lagrange orbitals are going to be interact. We are only deal with the metal d orbital. We are not including or we are not considering the Lagrange orbitals, okay, whether s or whether p, etc. Again, we cannot consider, as per the principle of what CFT, we can't consider the Lagrange orbital. One more is there. So again, there is a, if any pi bond containing ligands are there, again we can't explain that type of the bonding, and it failed to explain the relative strength of what the ligands now. And lastly the references. So these are the two quality books one can say, and many books are there. One is Principle of Inorganic Chemistry by Puri Sharma Kalia, and for coordination chemistry, so the R Gopalan, V Ramalingam, that's concise coordination chemistry by the Ramalingam. And these are the freely available, one can say, the online resources, that is NPTEL, Swayam, EPG Pathshala. These are very useful for UG as well as PG. So this is all about the crystal field theory. These are the some aspects, the usefulness of what the crystal field theory and the limitation also. Okay, so thank you for watching this. Stay connected with us. Thank you.